Thank you so much. All right, welcome everyone. Thank you very much for listening to my talk. It's on validation and utilization of physics-based simulated ground motions for bridge performance assessment. It's a mouthful, but basically we want to see if we can use physics-based simulated ground motions to assess bridge response. The work is done by myself and Mesa Dabbaghi from American University of Beirut, and we had two students working on the project, Jawad Fayyaz and Sarah Azar. So starting slide, acknowledgement from all the good work that we have done in the past few years with help of Caltrans, Peer, and in this particular project, it's a work that we did with SCEC, Southern California Earthquake Center. And during the, as you can see in the slides and the dates of these projects, we have developed a relatively good background in bridge modeling and bridge response assessment. And while we're talking with SCEC folks on validating their simulated ground motions, we thought this is like a match made in heaven. We can use our knowledge and use their in bridge modeling and response assessment and their simulated ground motion and see if these simulations are good enough. So what you're going to hear from me is all about this form of research. For today, I'm going to talk a little bit, like one or two slides about the need for simulated ground motions. I know that in the afternoon, David is going to talk about the Pacific Rim workshop, which he's going to provide more information and background about what is the need and where these simulated ground motions can be used. I'm going to talk one slide about how ground motions are simulated, different schools of thought on that. And again, I'm going to leave much more to David in the afternoon. And then I'm going to dive into what we have done in this project and give you some message to take home. And the arrows. All right. So the need for simulated ground motions, as everybody knows, we have gaps in our databases. There is no large magnitude, short distance. I cannot say there is no, but there is really scarce. And we need these form of ground motions to tailor seismic loading on our structures. One of the good things that can happen with simulated ground motions is that you can tailor them for the location of your site. But more importantly, and this is where the impact of simulated ground motions can come in, is that they can truly capture the spatial variability of seismic loading. And this can be used for performance assessment of portfolios or for earthquake early warning preparedness. And I specifically use the word preparedness here because this can be earthquake early warning systems that can tell you what's going to happen before the seismic waves arrive, but it can also provide you for means and ways to do structural control while a ground motion is happening. And for that, we're going to leave discussions with the projects that we are proposing on that line. Now, in terms of simulating ground motions, there are two schools of thoughts. Site-based models and source-based models. Site-based models, known as stochastic models, started from the work that Van Mark in the 1970s, tried to simulate ground motions that match a target velocity spectrum, and the recent work that Armin has done with his students, the Sanaz with Zareian, Mesa Dabbaghi, and others, to simulate, stochastically simulate ground motions for target magnitude, distance, PS30, and some information about the near fault parameters. On the flip side, the physics-based ground motions are much more elaborate in terms of modeling the rupture, propagating that rupture through a velocity model, adding a site response on top of that, and getting the ground motion on a grid. It takes much higher computational power compared to the stochastic ways of simulating ground motions. And hopefully it can result in features that the stochastic ways cannot capture. Our work is very much related to this physics-based method for simulating ground motions, although we're going to use the parameters that are used for the stochastic way of simulating ground motions for our validation. I'm going to elaborate on that further as I go forward. Now, there are two major platforms for simulating ground motions. CyberShake, which basically has all the possible magnitude rupture scenarios that you have in Southern California with a huge grid. And the intention was to develop hazard curves for Southern California. And they have done a lot of comparison with the hazard curves that is received from GMPs. There is a table here that shows the major differences between CyberShake and the other platform that is called the broadband platform. CyberShake is 3D, broadband is 1D. CyberShake needs to run on a supercomputer. You don't have access to it. Broadband can run on your personal machine. You need to contact folks at Skeg to get a username and password that you can run that type of simulation. And there are a lot of comparisons between the two. Workshops are happening. So if you guys are aware of these, great. If not, please contact me or Christine Goulet and other folks at Skeg that you can get involved in this line of research and discussion. Now, the intention of our work is validation. And this is a slide that I have borrowed from, the picture I've borrowed from Overkamp and coworkers, talking about the difference between verification, validation, and other things related to comparing computer models with reality. Our work is focused here. We have the reality, and that means what happened in the past earthquakes. And we have a computerized model coming from Skeg, and we want to do this validation to see if reality and the computer's model go together. In this, I'm doing a lot of thinking and let's say discussion with colleagues is that any form of validation should be independent of the simulation method. So it shouldn't matter if I simulated a ground motion or maybe Tara has a method for simulating ground motions. The way that we're going to do the validation should be fair and should be independent of the method. But maybe the way that I simulated ground motions is focusing on the period range, and I'm using a very loose terminology here, like short period for bridges, that does a good job in that zone. If it's missing long period, which means that my ground motion simulation method cannot be used for assessing response of very tall buildings, that should be okay. I can claim that my simulation method can be used for that engineering application. And with that, any validation method should have these four steps: identify validation parameters, obtain best estimate, compare these best estimate with what you get from simulations, and make a judgment from them. Very simple. Now, having this background, coming to the way that we have done validation of simulated ground motions the past 10 years with the folks at Skeg, specifically, there is a technical activity group called GMSV, an acronym for ground motion simulation validation. Yeah. And it started from type 0. This is like 15 years ago. There were some wiggles, velocity wiggles that were velocity histories that were generated from simulation of Northridge. We have the true recording of Northridge at the same site. By comparing them and we see that the same ups and downs, we say that these are good enough. From there, we have these three true type of engineering validation rather than just visual validation of the simulated ground motions. Type 1 says, if I can replicate the same Northridge, I look at the waveform at Northridge, I look at the waveform from my simulations, I apply them to a lollipop system, I apply them to a building or bridge. If the responses are similar, I say that my model is good. There's a problem with this type of validation because there is so much uncertainty in getting the same Northridge. And that brings us to type 2 and type 3 type of validation. Type 2 is based on, it basically is saying, do simulated ground motions follow the same trend of recorded motions? In other words, what you get as an intensity measure for coming out of your simulation follows a GMPE. And this GMPE can be for an intensity measure, or the GMPE can be for a response. And the work that I'm going to present today is mostly at this type 2 validation. And by the way, we have a paper in BSSA that basically summarizes all of the work that I'm going to present today. And I heard Amarnath mentioning this morning that they need a peer report. And Amarnath, you're going to get your report very soon in the next couple of months. And finally, comparing ED in type 3, you're saying that I'm going to use simulations as a database. A database like NGA-WES2, you're going to borrow gram motions from it, select scale, and use these simulated gram motions in lieu of recordings to do the work for your project. Now, we're going to focus on type 2, and this would be the problem statement that we're going to address in this project. Can we develop an application flavored validation test for physics-based simulated gram motions? The answer is yes, we have done it here. And can we use physics-based simulated gram motions for performance assessment of ordinary bridges? We are moving towards and inching towards giving a yes answer to this. And talking about the R project. I want you guys to imagine 3 sets of variables. Event parameters, everybody are familiar with them, magnitude, distance, VS30, everything that goes into a GMP. There is response of a bridge. Imagine that this is an equivalent of ROD 50 SA, but instead of response of a single degree of freedom system, is a response of the column, is the column drift ratio. So the median of column drift ratio. There are some intermediate parameters. I mentioned earlier in my talk that there are, in these secondary variables, I borrowed from stochastic method, the stochastic approach for simulating gram motions. We are saying that we can do validations based on these intermediate parameters. Now, if I can show that there is similarity between, or this black box that takes from RZZ to EDP is similar between recording and simulations, and the theta to EDP is similar between recordings and simulations, I have proved that these RZZs are efficient and sufficient to predict validity of a gram motion. From that point forward, and for this particular application and gram motion simulation method, I can focus on RZZs, and if I can always show that the RZZs are matching between simulations and recording, I can validate that gram motion. It's a very simple concept. And the secondary concept that I want you to be familiar with is that we are saying we're generating, let's say, thousands or hundreds simulations from imagine that we're saying we're generating 100 simulations. The one recording that we have from nature, if it happens to be between ±2 sigma or any form of band that you suggest as your validation metric, that means that that recording belongs to the population of simulations. In other words, these simulations are capable of giving you a recording that nature gave us. Now, with this, let's talk about how we did the work. We looked back into the past 100 years of earthquakes in Southern California. We looked into the probability of magnitude and distance. And this is the table of those records. And I'm trying to go a little bit faster because I know I'm getting to the end of my time. We generated catalogs of earthquakes, 100 catalog of simulations that have conforming rupture distance distribution and magnitude distribution. So in other words, you can say we created an equivalent of Southern California 100 times in the past 100 years. So with this, I have 1 catalog of natural recording, 100 catalog of simulations. My intention is to show if this one of these recordings belongs to this population of simulations, my simulations are good enough. Now, in order to do this, we have bridge models, which all of our work so far, although we have finished the work for bridge F, but our focus has been for today's presentation is on bridge A, bridge B, and bridge C, which much of the periods are below 1 second. And once you go to the above 1 second, things are going to get a little bit different. It's out of the time that I have for today to discuss the results. Now, I mentioned about column drift ratio. We are applying gram motions, rotating them, and taking the median maximum maximum column drift ratio out of these rotations. So there's a lot of analysis done. I hope that we can discuss how we can reduce the time to run later in the discussion in OpenSeas. A little bit about these intermediate parameters. This is a recording of a ground motion waveform. You can develop the areas intensity, D595 between 5% and 95% areas intensity, where you're going to get to the median point is T mid. And there are two other parameters called F mid and F prime, which basically says what is the dominant frequency of the ground motion and how that frequency changes in time. We did a random forest approach and the Baruta algorithm to find out what are the major features of these RZ parameters that affect the response. And we have done a test of collinearity to find out, to make sure that there is no linear relationship between these parameters. We ended up with these set of RZZ parameters, we call them RZZIs. We think that these guys are enough to estimate EDPs. We have developed an equation to, I can skip the slide. Basically, I wanted to say that we have also looked into the correlation structure. We have developed an equation that takes rod D50, rod 50 CDR to these RZZ parameters. And in many cases, there's a really good match. The dot that you see in black is close to that 2575 quartile that you get from simulations. And this gives us a good feeling that areas intensity and duration are enough to predict the response. The offness in F mid is okay, given that the work that we have done in another project, realizing that frequency content is not an important thing for these bridges.
Farzin, if you're able to reach your conclusions, that would be wonderful.
Sure. I'm gonna zoom into these last slides. And we have done the theta to EDP comparisons. And let me get to the last slide. Probably what I can tell you that is that we have completed the RZZ to EDP, theta to EDP, and we see the same trends between theta to RZZ. In other words, the same effect from RZ to EDP is observed in theta to RZZ, and these RZZs can be used for validating the simulation. And this is the last slide that I want to talk about. Especially, I want to leave you with these two last bullet points, that the validation methodology evaluates ground motion simulations with these three relationships. And since we have observed that the mean relation from RZZ to EDP is consistent, theta to RZZ can be used to validate these simulations. And I'm sorry I went over time. I'll be happy to answer questions.